Hello everyone, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. Today I am going to give a lecture on electrical circuit and networks. So the subject is module designed for the second year Diploma Electrical Engineering students, and I'm going to give lectures on the topic of Unit 2, 3 and 4, and my today's topic of discussion is Phasor diagram and impedance triangle of series RLC circuit. So previous lecture I already told you that how to draw the Phasor diagram of RL circuit, series RL circuit, how to draw the Phasor diagram of series RC circuit. Then I discuss on the process to draw the impedance triangle of RL circuit, impedance triangle of RC circuit, series RC circuit. So with the help of the previous two lecture, I'm going to show you that how to develop or draw the Phasor diagram and impedance triangle of series RLC circuit. RLC means resistor, inductor and capacitor. If all these three elements are connected in a circuit in series, then that type of circuit is called the RLC circuit. Look, on the right side top corner, a circuit is given here. So what is the name of this circuit? You all know this circuit is called the series RLC circuit. Why it is series RLC circuit? Because resistance, inductance and capacitance, all the three elements are connected in series with the supply voltage V. So V voltage here is Vm sin omega t, sinusoidal voltage. Now in this circuit, the voltage, the applied voltage is V. This is the total voltage. And the voltage drop across the resistor is VR. The voltage drop across the inductor is VL, and the voltage drop across the capacitor is VC. So I wish up to this you all are clear about the topic. Look, now so this is actually the explanation of this given RLC circuit. Now in the RLC series circuit, what is XL? You all know XL is actually omega L. We all know that XL is called the capacitive reactance, that is omega L. So what is omega? Omega is 2 pi f into L. So it is directly written here. XL equals to 2 pi f into L. And what is XC? XC is, you all know that XC is 1 by omega C. I already talked on this topic in my first few lecture of this chapter. So what is omega? Same 2 pi f and c. So this part is written here. X equals to 1 by 2 pi fc. Is it clear now? Yes, I think it's clear to all of you right now. Now, what is VR? So VR here is IR, that is the voltage drop across the resistor because the current is I. So VR is I into R as per Ohm's law. IR, that is the voltage across the resistor R and is in phase with current I. So no problem, using Ohm's law simply we can say that VR equals to IR. What is VL? VL is the voltage drop across the inductor. We know that VL equals to IXL. So no problem with this part also. VL equals to IXL. That is the voltage across the inductor L. And it leads the current I by an angle of 90 degree. Because we know that for purely inductive circuit, voltage always lead from the current. In other words, we can say that the current always lags behind the voltage if it is an inductive circuit. So for that reason, it is written VL equals to IXL. That is the voltage across the inductance L, and it leads the voltage is leads the current by an angle of 90 degrees. The third one is VC. What is VC? VC equals to I of XC. VC equals to IXC. That is the voltage across capacitor C, and it lags the current I by an angle of 90 degree. If it is a purely capacitive circuit, then we know that for the capacitor, the capacitive voltage always lags behind the current. Or in other words, you can say for a capacitive circuit, current leading from the voltage. So V equals to IXC, that is the voltage across capacitor C, and it lags the current I by an angle 90 degree. So all these three is already explained in the previous lecture. I'm just giving you a recall of this for a better understanding for the next part. Now, let me show you how to draw a phasor diagram of RLC circuit. So in the same way, we are considering I as our reference phase along x-axis. Then for VL and VC, here we consider that VL is greater than VC. So if this is the reference phase I, then VL value is higher than VC. So what will happen for inductor? For inductor, the voltage is leading from the current I, 90 degree leading. And for capacitor, the voltage is lagging from the current at an angle 90 degree. So now if we consider that from 0 to this particular portion, because here VL is greater than VC, so we have to take only the phasor which is along VL, because here VL is greater than VC. So what will be the value? The value will be VL minus VC. So that value will be there. Now draw AB parallel with OVL, and this OVL is VL minus VC, this part. And if we consider it is this point is suppose W, then BW is, we have to draw BW parallel with AO. Then the OB will be the resultant vector of OA and AB. So in this way, we can draw the phasor diagram of a series RLC circuit where AB is the vector VL minus VC, that is IXL minus IXC, and OA is the voltage across the resistors. So OA is VR phasor and AB is VL minus VC phasor. So the summation of these two, vector summation of OA plus AB, is actually the applied voltage V equals to IZ, and we are considering that the angle between the applied voltage and the voltage across the resistor is phi. So this is the process to draw the phasor diagram of a series RLC circuit. Now, just the topic I discussed in the previous slide, that is written here. Step to draw the phasor diagram of the series RLC circuit. Take current I as reference as shown in the figure below. So we consider here current I. The voltage across the inductor L, that is VL, is lead the current I by 90-degree angle. That is also considered in this way. VL along positive y axis and I was along positive x axis. Next, number 3. The voltage across the capacitor, that C is VC, is drawn lagging the current I by 90-degree angle, because in capacitive load the current leads the voltage by an angle 90 degree. That part is also covered. And finally, the two vector VL and VC are opposite to each other. Now the question is, how can we find this applied voltage? Applied voltage is the summation of VR plus, so it's simple, the Pythagoras. So what is V? So V square equals to, you can say VR square plus VL minus VC whole square. Very simple. So that is written here, VR square plus VL minus VC whole square. So what is VR? VR is IR square plus what is VL? IXL. What is VC? IXC. So after the simple calculation, we can say that V equals to I is the common from all the part. So and we take it outside the root over. So inside the root over it was I square. So I square and root omitting, we take only I root over R square plus XL minus X whole square. Or from here, from this equation, we can say that I equals to V divided by root over R square plus XL minus X whole square. So this is actually Z. So we can say that V by Z, where Z equals to root over R square plus XL minus X whole square. So in this way, we can find the applied voltage magnitude. And now try to understand the phase angle. Can you remember that what was the phasor? This was the current phasor. This is the this is the VR. This was VR along x-axis, and this and this one is the VL minus VC. Just try to understand. This is V R phasor, right? This is the voltage phasor. VR. This is the VR is actually the voltage drop across the resistor. This is V, the applied voltage, and this is VL minus VC. This is the angle of phi. Now, what is tan phi? Tan phi is VL minus VC by VR. Very simple. VL minus VC by VR. We write here. Now, why we are writing this XL minus XC by R? Because what is VL? VL equals to I into XL. What is XC? VC equals to X into I. And what is VR? VR equals to I into R. So after putting all these three values, VL equals to IXL minus IXC by IR. So we find the value that is where phi equals to tan inverse XL minus XC by R. So in this way, we can find the phasor angle also. Now, the power in RLC series circuit. Look here, the product of voltage and current is defined as power. We know that the active power equation P equals to VI cos phi. That is also equals to I square R, where cos phi is the power factor of the circuit and is expressed as cos phi equals to VR by V. So from where it is VR by V, again try to remember. This was the angle, and then this was phi. So this is VR, and this one was V. So what is cos phi? Cos phi is nothing but VR by V. And also we can explain that cos phi equals to R by Z. How we can explain? Because V equals to I into Z. Think everything is going fine. And what is VR? I into R along this axis. So if we delete everything, so what will happen? The thing that will happen, that is, this is R, this is Z. So this is phi. So what is cos phi? R by Z. From this triangle, we can prove that cos phi equals to VR by V or R by Z, and this formula will help you to solve different types of problem related with these RLC circuits. Please try to remember this, and this is actually the explanation of all these factors. Now, the three cases of RLC series circuit. So just take a look of it. When XL greater than XC, and the phase angle phi is positive, the circuit behaves as RL series circuit. Please note it. Very important MCQ type question or interview type question, in which the current lags behind the applied voltage and the power factor is lagging power factor. When XL is greater than XC, these are the factors which is happening. When XL is less than XC, the phasor angle phi is negative. This is negative, and the current acts as a series RC circuit. So when XL is greater than XL, X is greater than XL, then series AC circuit. When XL is greater than XC, is acting as a RL series circuit. And then for XL less than XC, which is the current leads. So here what will happen? The current leads the voltage by an angle 90 degrees. So these are the factors happening when the value, we have to find that whether XL is greater or XC is greater. This is the important topic. Now when XL equals to XC, then what will happen? The most important topic. Everything is important, no doubt, but this is a well-known question. When XL is equals to XC, then the phase angle phi is 0. Yes, XL is equals to XL. The phase angle phi is 0 because no phase angle will be there. If this is the phase, suppose no, x-axis, y-axis, these two is same value. So this is our VL minus VC, something like this. VL, VC. So both are same, so no value will get taken from here. So what will happen in this case? The current behaves like a purely resistive circuit. So only resistance will be there in the circuit if VL minus XL minus XC is equals to XL and XC is equal. In this type of circuit, the current and voltage are in phase with each other. The value of the power factor is unity. Okay, because cos phi equals to 0. So what will be the value of the power factor? You know that cos 0 equals to 1. For that reason, when XL equals to XC, please try to remember that the power factor is always unity. Now, look, I already talked about this, but for the clarification, I'm again impedance triangle of a RLC series circuit. Fine. If the inductive reactance is greater than the capacitive reactance, that is XL greater than XC, and inductive, then the circuit reactance is inductive, giving a lagging phase angle. So it's a lagging phase angle. Fine. ZR. When lagging phase angle, inductive reactance is greater than the capacitive reactance. So remember these two parts. Inductive reactance, what is greater than the capacitive reactance? Now, it's a lagging phase angle. Here, for this diagram, impedance triangle is shown below when the circuit acts as a RC circuit. So in this case, if XL is less than XC, then this will be the figure. And here, the current is leading. It's a leading power factor. XC minus XL. Now let me talk about the application of RLC series circuit. It has different types of application, but here it acts as a variable tuned circuit, one of the important application. Next, the second application, it acts as a low pass, high pass, band stop filters, depending upon the types of frequency. Yes, so it has a huge application for the filter. So it's at in different way, low and low pass, at high pass, band stop, like this. Number 3 application, the circuit also works as an oscillator. A very useful point, act an oscillator. And then voltage multiply and pulse discharge circuit. Act as an voltage multiply and pulse discharge circuit. Voltage multiplier and pulse discharge circuit. So these are the application. Now I think for today's lecture, my task is completed. So that's all about the RLC circuit. If you have any doubt, you can contact with me to clear that. Just go through the books that will give you more concept, and also try to solve the problem more and more. That will help you to build up your knowledge about this circuit analysis. Now this is the reference which helps me a lot to develop this lecture. Thank you all. Goodbye.